Hello and welcome to STAAD.Pro training courses. Today we will see how to specify a geometric nonlinear analysis. Our session is split in three parts. We will start by giving a brief definition of geometric nonlinear analysis. Next we will see its implementation in STAAD.Pro, the possibilities and the limitations. And finally we will run a simple application example to illustrate the specific steps for this type of analysis. Nonlinearity can relate to one or more factors. We can see here it could be due to the geometry, to the material, to the boundary conditions, or the loads. Today we will consider only the geometric nonlinearity problem. The solution of nonlinearity problem requires numerical approach. Essentially, this method consists of incrementing the load and iterating for successive corrections until equilibrium is achieved. Here we use the well-known Newton-Raphson method or the modified form of it. The very nature of a numerical approach is that it is an approximation. So when a solution is possible, the convergence will depend on various parameters controlled by the user, and this is what we'll see in the next session. Before we go further, it is important to remember the difference between load combinations and primary loads. If we consider the case on the screen, in a fully linear analysis, both cases will lead to the same results by virtue of the principle of superimposition. In a nonlinear analysis, superimposition principle does not apply. The nonlinear effect will only be captured if we analyze the case where all the loads are acting concurrently. And here's the difference. Only primary load cases are analyzed. Load combinations are just algebraic combinations of individual load cases. So traditional load combination should be used in a linear elastic analysis only. In a nonlinear analysis, one would need to create new primary load cases that combine basic primary load cases. And this is made easier using the repeat load command. Let's see now the parameters that are available to the user. The analysis of the first load step must be stable. If this is not the case, then the parameter arc should be used to control and prevent this instability. The iteration parameter is used to set the maximum number of iterations, and this is with the objective of avoiding infinite number of iterations. By default, it's 100. The user will need to check that the maximum number has not been attained, otherwise he would need to increase that number. The tolerance is the criteria by which the program will decide if the solution has converged or not. A reasonable value should be selected by the user to help the program converge. The step parameter defines the number of load increments. A higher number could help in the case of large displacements or rotations, but higher number also means an increase in the analysis time. The rebuild parameter will indicate the frequency at which the solver will need to update the stiffness matrix. A value of 0 means that the update will happen only at the start of each load step. A value of 1 will mean that at every iteration, the stiffness matrix will need to be updated. Finally, the parameter kg will let the user decide whether geometric stiffness should be added or not to the stiffness matrix. Additional parameters are also available to monitor the displacement of a given node. The user will, in this case, need to specify the node number, the degree of freedom, and the target value in the current units. Once the target value is reached or exceeded, the load increment stops, the analysis is terminated, and the results are reported for the applied load. Once the analysis is complete, the user has access to the post-processing mode to review the usual results. There is, however, a specific layout for nonlinear analysis through which the user can display graphs of node displacements or beam forces for each load increment. The program generates as well two text files with all incremental values for the node displacements and for the beam forces. Let us now see a practical example on STAAD.Pro. Okay, here we have a simple structure. All the properties of this structure have been already defined. We need now to make sure that the loadings are correctly defined. I already created two load cases, one for a vertical force and a separate load case for the horizontal force. Now I said earlier that if we want to analyze the behavior of the structure under the two loads acting concurrently, so we need to create a third load case, which will be a primary load case. Remember, only primary load cases are analyzed. So, and in that load case, we would have to combine the two forces. So let's go ahead and use the repeat command that will make it easier for us. We first start by creating our primary load case. Let's call it V plus H. And let's combine the two existing primary loads. So we pick here the repeat load and we select both load cases with a factor of 1 and we just add. And here we go, we now have our third load case, which is combining the two previously created load cases. Okay, now that the loads have been defined, we need to insert the analysis commands. With the nonlinear analysis, we need to insert a command after each of the load cases. So let's go ahead and start with that. So we can pick one load case here, define command. We select it so that we make sure that the command is inserted correctly after the load case or before the load case. So here we click on this, we check this box after current, we select the nonlinear analysis, we keep the default values, we'll change only the load steps. If you will leave it at 1, that means that we want the load to be applied fully at once. And we add. Change. After each command, we need to add a change command. The change command will instruct the program to reset the stiffness matrix before proceeding with the next load case. And add. And here we go. So this analysis is related to the first load case. We do the same for the last load, for the second load case. Define commands after current, nonlinear, and we change the load steps to 5, and we add, and we do the same with the change command. We add. And we finish with the load case number 3. So we pick on the command that is right after the load case, and it will be inserted before. Okay, after nonlinear, 5, and add. And finally, the change command, add. Okay. And now we close, and we can save. There is one more command we need to insert whenever we deal with multiple analysis. The command is setNL, NL for number of load cases. We need to inform the program of the total number of primary load cases before it starts the analysis. This way, the program will set aside additional memory for further post-processing. So to insert this command, we can just, while we are in the analysis and design ribbon, miscellaneous commands, and we have set NL here. So the number of this NL should be at the minimum the same number as the primary load, as the number of the primary loads. We have 3 primary cases, so it should be 3 minimum, but we could also have a larger number like 5 in the case we need to add, or we plan to add additional load cases later. So okay. And you can see the setNL command here inserted at the very beginning of your file. We can save here. Okay. We're now ready to run the analysis. So let's go ahead. In the design and analysis ribbon, we select Run Analysis. Before you close this window, make sure that you have not exceeded the maximum number of iterations in any of the load cases. Otherwise, you would have to increase that maximum number of iterations to make sure that you are converging in all load cases. So nothing specific here. We can move ahead and go to the post-processing mode. Here we have access to all common types of results. So again, displacements, reactions, and so on. All the results are given for the last load step. Okay. There are, however, 2 types of results that are available for the geometric nonlinearity. These are graphs and tables detailing the node displacement variation with the load step and the beam forces variation versus the load step. We can go ahead and check this one. You select your node on the graph on the table, okay, and the curve is displayed. So this curve is describing how the displacement is evolving with the load level. We are seeing here displacements in the y direction. If you want to see in any other direction, just right click, you select diagrams, and you select the direction you are interested in. Okay. The other types of results we have are in the form of text files. These text files can be found in the same folder where the STAAD input file is residing. They have the same name, but an additional suffix. So this one is for the joint displacement. It details the evolution of the joint displacement for every load case and for each load step. Okay. So if you want to follow the progression of the node displacements. Likewise, we have another file for the member forces. So again, the same file name with a different suffix. This concludes our training session for the day. Thank you for following us. See you next time.